There is a moment, a specific, calculable, irreversible moment when the door closes. Not a metaphorical door, not a philosophical one, a real, gravitational, orbital-mechanical door. A door defined by the positions of two planets, the curvature of space-time, and the hard arithmetic of rocket fuel. Once that door closes, it doesn't reopen for another 2 years and 2 months. And if you are on the wrong side of it, if you are standing on the red dust of Mars when it swings shut, then you are staying. Not because anyone decided that, not because the mission failed, but because the universe, indifferent and precise, has moved the exit out of reach. This is the story of that door. And of the 9 months that precede it, the 9 months during which every decision made by a crew of human beings hundreds of millions of miles from home will either keep them alive or seal their fate. We are going to walk through that window together. We are going to feel what it means to be inside it, counting down, watching the orbital mechanics tick forward with the same indifference a clock shows as midnight approaches. And we are going to understand, in a way that most people never fully grasp, just how precisely calibrated a human life has to be to survive on another planet, and just how many ways that calibration can fail. But first, we need to understand the clock itself. Because before the 9-month survival window even begins, there is a longer, stranger clock already running, a clock that started ticking the moment humanity first looked at Mars and wondered whether we could reach it. And that clock runs on something that has nothing to do with human ambition or technological capability. It runs on gravity. It runs on orbital resonance. It runs on the patient, mechanical mathematics of two planets circling the same star. Mars and Earth are not neighbours in any fixed sense. They are two runners on concentric tracks, circling the same point at different speeds. Earth, the inner runner, completes its lap in 365 days. Mars, on the wider outer track, takes 687 Earth days. Because of this difference, their relative positions change constantly. Sometimes they are on the same side of the Sun, separated by as little as 54.6 million kilometers, a gap that, in cosmic terms, is almost intimate. Other times they are on opposite sides of the Sun, separated by more than 400 million kilometers, with our star sitting squarely between them like a wall of nuclear fire. The rhythm of this dance produces something called a synodic period, the time it takes for Earth and Mars to return to the same relative configuration. That period is approximately 780 days, or just over 2 years. This means that roughly every 26 months Earth and Mars come back into favourable alignment. Every 26 months a launch window opens. A corridor through the solar system becomes traversable with the minimum expenditure of fuel and the maximum chance of arrival. Miss the window and you are not waiting weeks. You are waiting more than 2 years for the next one. For unmanned missions, this 26-month rhythm is an inconvenience. Rovers and orbiters don't care. If a spacecraft misses one window, engineers recalculate, reschedule, and wait. The machine doesn't age. The machine doesn't need food or water. The machine doesn't get frightened or lonely or sick. But for human beings, the 26-month rhythm is not an inconvenience. It is a trap. Because it means that once you leave, once you commit to the trajectory, once you light the engines and push away from Earth's gravitational embrace on the long curved arc toward Mars, you cannot simply turn around if something goes wrong. You cannot cut the mission short on a whim or an emergency. The orbital mechanics don't care that your water recycler has failed, or that a crew member has developed appendicitis, or that a solar flare has torn through your habitat's radiation shielding. The planets will be where they will be. The fuel you have is the fuel you have. Turning back early or coming home before the return window opens requires a quantity of propellant that no spacecraft we have ever built or are currently planning to build can carry. So, there it is. The first constraint, the deepest constraint. Before any human being sets foot on Mars, before the first bootprint is pressed into ochre soil, the mission is already locked into a timeline that is not written in a mission plan, but in the orbital mechanics of the solar system itself. You go when the window opens, you stay until the return window opens, and between those two events, you survive, or you don't. The journey to Mars, depending on the launch window and the trajectory chosen, takes somewhere between 6 and 9 months. Then, assuming an opposition-class mission, the most practical architecture for early crewed missions, the crew spends approximately 500 days on the Martian surface, waiting for the planets to realign for the return trip. Then, another 6 to 9 months back to Earth. The total mission duration from departure to return runs somewhere between 2.5 and 3 years, depending on the specific orbital geometry of the launch year. But within that larger arc, there is a critical inner window, a 9-month period on the surface of Mars during which the compounding of risks, the degradation of systems, the slow erosion of human physiology, and the creeping possibility of catastrophic failure all reach their peak. It is the window between landing and the opening of the return launch opportunity. 9 months during which a crew must maintain every life-critical system, protect every fragile human body, make every correct decision, not once, not twice, but continuously, every single day, with no rescue possible, no resupply arriving, and no margin for the kind of errors that on Earth we simply call learning experiences. On Earth, a learning experience is a story you tell later at dinner. On Mars, during the 9-month window, a learning experience is often just the last thing that happens. To understand why, you have to understand the environment they are living in. Not in the abstract way that science documentaries usually describe it, not as a set of statistics about atmospheric pressure and average temperature. You have to understand it the way a crew member would understand it. Waking up on day 1 of surface operations, feeling the full weight of where they are and what surrounds them on all sides. The Martian atmosphere is approximately 95% carbon dioxide. It is less than 1% as dense as Earth's atmosphere at sea level. This means it provides almost no protection against radiation. It means the pressure outside the habitat is so low that exposed human tissue would begin to swell and rupture within seconds. It means that the ambient temperature, which swings from roughly minus 80 degrees Celsius at night to perhaps 20 degrees Celsius at the equator during a warm afternoon, is not a weather inconvenience, but a survival parameter that the habitat must actively manage every hour of every day. The surface itself is coated in a substance called perchlorate, a toxic chemical compound that permeates the Martian regolith in concentrations that would, over time, suppress thyroid function in humans and cause other serious physiological damage if ingested or inhaled in sufficient quantities. The fine dust that coats everything, that rises in planet-wide storms capable of blocking sunlight for weeks at a stretch, carries this perchlorate into every seam, every airlock, every filtration system. It is not merely an inconvenience, it is a slow poison that the crew must actively manage every single day through rigorous decontamination protocols that cannot be skipped, cannot be rushed, and cannot be allowed to degrade through familiarity or fatigue. And then there is the radiation. Mars has no global magnetic field. Earth's magnetic field deflects a significant portion of the charged particles that stream continuously from the Sun and from distant galactic sources. On Earth, we live inside a vast invisible shield that we never think about and never notice. On Mars, that shield does not exist. Galactic cosmic rays, high-energy particles originating from supernovae and other violent events across the galaxy, penetrate the thin Martian atmosphere almost unimpeded and reach the surface with enough energy to pass through the walls of a habitat, through the soft tissue of a human body, through the DNA of individual cells, breaking chemical bonds and triggering mutations in ways that accumulate silently over months and years. NASA's current career radiation limit for astronauts, the total dose beyond which the increased lifetime cancer risk is considered unacceptable, would be approached or exceeded during a single Mars mission under current shielding technologies. The 9 months on the surface represent the largest single contribution to that cumulative dose. Every day spent on Mars is a day of radiation exposure that cannot be undone, cannot be metabolized away, and adds permanently to the biological ledger that every crew member carries in their cells. This is the environment. This is where the 9-month clock is ticking, but the environment, as brutal as it is not the most immediate threat. The most immediate threat, the one that keeps mission planners awake at night more than any other single factor, is the life support system. Everything that keeps a human being alive on Mars is mechanical. Every breath of oxygen is either carried from Earth, extracted from the Martian atmosphere through a power-intensive chemical process, or produced by a system of electrolysis that splits water molecules into hydrogen and oxygen using electrical power drawn from solar panels or a nuclear reactor. Every sip of water is recycled, processed, filtered, and reclaimed from urine, sweat, exhaled breath, and every other source of moisture the habitat can capture. Every calorie of food is either carried from Earth in carefully portioned packages or, in more ambitious mission architectures, grown in controlled agricultural modules where lighting, temperature, humidity, and atmospheric composition must be maintained within narrow bands to keep the plants alive. None of these systems, not one, has a natural backup. On Earth, if your water system fails, you walk to the river. If your food supply runs low, you drive to the store. If the air in your building becomes unbreathable, you open a window. On Mars, if your oxygen generation system fails, you have the oxygen currently in the habitat, plus whatever is stored in emergency tanks. That is your entire supply. You fix the system, or you die. You fix it correctly, with the tools and parts you have, with the knowledge and skills of the crew members who are present, within the time your emergency reserves allow. There is no calling for help. There is no technician who can be dispatched. There is no supply ship that can arrive within the critical time frame. Communication with Earth, at the distances involved during the 9-month window, has a time delay that ranges from approximately 3 minutes when Mars and Earth are at their closest to over 20 minutes when the planets are further apart. To complete blackout during solar conjunction, when the Sun interposes itself directly between the two planets, and radio communication becomes impossible for days or weeks at a time. This means that even in the best-case scenario, asking Earth for help with a technical problem involves sending a question and then waiting 6 to 40 minutes for an answer to begin arriving back. In a crisis, in the kind of rapid onset emergency where a decision must be made in seconds, not minutes, the crew on Mars is operationally alone, completely and absolutely alone. Earth can watch, Earth can advise. With a 20-minute delay, Earth cannot help. This reality, the aloneness of it, is something that is easy to state and almost impossible to fully internalize. We live in a world of instant communication, of always available expertise, of emergency services that can arrive within minutes. The psychological infrastructure of modern life is built on the assumption that help exists and that it can reach you. A crew on Mars, inside the 9-month window, must rebuild their entire psychological relationship with safety and rescue from scratch. They must function as a fully self-sufficient civilization of 4 to 6 people, capable of diagnosing and repairing any system failure, treating any medical emergency, resolving any interpersonal crisis, and making any critical decision entirely from within their own collective knowledge and capability. The psychological weight of this is not theoretical. It is one of the most intensively studied aspects of long-duration spaceflight, and the research is humbling. Studies of crews in isolated, confined environments, Antarctic research stations, submarine deployments, the International Space Station, consistently find that the psychological challenges of long-duration isolation are not merely unpleasant. They are operationally dangerous. Cognitive performance declines, decision-making quality degrades, interpersonal conflicts escalate. The conditions that produce errors, fatigue, monotony, stress, grief, fear, accumulate over months in ways that no amount of pre-mission screening and training can fully prevent. On a 9-month Mars surface day, these psychological dynamics are not background noise. They are a primary survival variable. A crew that cannot maintain functional cohesion, that fractures into conflict, that experiences a critical breakdown in trust or communication, is a crew that begins making the kinds of small, compounding errors that on Earth would be correctable, and on Mars are potentially lethal. And we haven't even talked yet about the medical risks. We haven't talked about what happens when someone gets seriously ill, not space sick, not fatigued, but genuinely, acutely, medically ill, in an environment where the nearest surgeon is 20 light minutes away, and the nearest hospital is tens of millions of miles across the void. We haven't talked about bone density loss, which proceeds on Mars at a rate that makes even the well-documented bone loss of the International Space Station look modest by comparison. We haven't talked about the vision problems that a significant percentage of long-duration space travelers develop, caused by fluid shifts in the body under microgravity and low-gravity conditions that alter the structure of the eye and the pressure around the optic nerve in ways we still do not fully understand. We haven't talked about the immune system suppression that occurs during spaceflight, or the disruption to the gut microbiome, or the cardiovascular changes that begin within days of leaving Earth's gravity well and continue throughout the mission. We haven't talked about any of that yet, and all of that is coming. But for now, in this first part of the story, what matters is that you understand the basic architecture of the problem, that you feel, in your body, the shape of what a crew on Mars is facing during the 9-month window. They have arrived, the spacecraft has landed, the habitat is pressurized, and the life support systems are running. The crew has stepped outside in their suits for the first time and looked at the horizon. The actual Martian horizon, rust-red and impossibly close, because Mars is a smaller planet and its horizon curves away more sharply than Earth's. And they have felt, presumably, some version of the awe that the first humans to set foot on another world would inevitably feel in that moment. And then the clock starts. Not metaphorically, literally. A countdown timer is running in mission control on Earth, and in the crew's own operational planning systems, marking the days until the return launch window opens. That window, once it arrives, will remain open for only a limited time, perhaps a few weeks at most, before the orbital geometry shifts again and the exit closes. Miss it, and the crew waits another 2 years for the next one. Miss it with a failing life support system, or a crew member who is gravely ill, or a habitat that has been compromised by a dust storm or a micrometeorite impact, and the consequences become very quickly unsurvivable. 9 months. That is the window. From day one on the surface to the day the return rocket fires its engines, approximately 270 days will pass. Some missions will be longer, some will stretch toward 500 days on the surface. But the critical window, the survival window, the window during which the maximum number of critical systems must perform without failure, and the maximum number of human bodies must remain functional, and the maximum number of correct decisions must be made, that window is the first 270 days, because those are the days before the first return opportunity. Those are the days when being rescued is definitionally impossible. Those are the days that decide everything. In the parts that follow, we are going to walk through that window in detail. We are going to look at each of the major threat categories, the life support systems, the medical vulnerabilities, the psychological risks, the environmental hazards, the communication constraints, and we are going to understand not just what they are, but when they become critical, how they interact with each other, and what the compounding of multiple simultaneous stresses looks like in practice, because that is the thing that the statistics don't capture, and that the engineering simulations only partially model. The real danger of the 9-month window is not any single threat. It is the simultaneity. It is the way a dust storm that degrades your solar power also stresses your climate control system, also increases crew confinement, also elevates psychological tension, also degrades sleep quality, also reduces cognitive performance, also increases the probability of operational errors at exactly the moment when the environmental challenges require the crew to be performing at their best. It is the feedback loops. It is the compounding. It is the way that on Mars, unlike on Earth, there is no slack in the system, no reserve of redundancy deep enough to absorb multiple simultaneous failures. No outside help arriving to relieve the pressure, just the crew, the habitat, the equipment, and the clock. Day one of the window is the first breath of Martian air, filtered, recycled, maintained. It tastes reportedly like the inside of a spacecraft, which is to say slightly metallic, slightly stale, deeply familiar by now after months of transit. The crew knows this air. They have been breathing a version of it since they left Earth orbit. But this air is different. This air is all there is. The refill truck is not coming. The supply ship is 9 months in the future, at the earliest. This air, this water, this food, these systems, this is the entire universe of survival resources available to these human beings for the foreseeable future. The clock is running. How long can they last? That is what we are here to find out. On the 37th day of surface operations, according to one of NASA's most detailed Mars mission simulation studies, the first serious psychological friction event occurs. Not on day one, when the adrenaline of arrival is still flooding every waking moment. Not on day 10, when the novelty of the surface is still sustaining the crew's emotional energy. Day 37. 5 weeks and 2 days into the 9-month window. The moment when the extraordinary has become ordinary, the horizon has stopped being miraculous, and the weight of how much time remains begins to settle into the crew's daily experience, like sediment settling to the bottom of still water. 37 days in and roughly 233 days still to go before the return window opens. This moment, the transition from awe to endurance, is one of the most studied and least publicly discussed aspects of long-duration spaceflight psychology. Researchers call it the third quarter phenomenon, though on a Mars mission it arrives earlier than the name implies. It is the phase when the initial excitement of departure has long since faded, the destination has become familiar, and the return home still feels impossibly distant. Time stops feeling like it is moving towards something and starts feeling like it is simply accumulating. Days stop being adventures and start being shifts. The habitat stops being a marvel of engineering and starts being a box. What makes this psychologically dangerous is not the discomfort itself. Human beings can endure remarkable discomfort. What makes it dangerous is what it does to attention, to motivation, to the quality of the small daily decisions that, on Mars, are never actually small. To understand the full picture of what a crew faces during the 9-month window, you have to hold two timescales in your mind simultaneously. There is the macro timescale, the 270-day countdown to the return window, the slow arc of the mission from landing to departure. And then there is the micro timescale, the daily, hourly, minute-by-minute texture of life inside the habitat, where the immediate practical demands of survival are constant and relentless, and only imperfectly compatible with the psychological needs of the human beings trying to meet them. The habitat itself is the starting point for understanding the micro timescale, because the habitat is not a home. It is not even close to a home. It is a pressurized container, a cylinder or series of connected modules with a total habitable volume that current mission architectures estimate at somewhere between 70 and 250 cubic meters for a crew of 4 to 6 people. To put that in terms that mean something physically, the lower end of that range is roughly the interior space of a large recreational vehicle. The upper end is approximately the floor space of a modest 3-bedroom house, except that it is not a house. It has no windows that can be opened, no outdoors that can be accessed without a 45-minute suit-donning procedure, no separation between the space where you work and the space where you sleep and the space where you eat and the space where you exercise and the space where you try, against considerable odds, to maintain some version of privacy and personal identity. Every person who has spent extended time in confined, isolated environments, polar researchers, submariners, ISS astronauts, reports the same thing. The confinement itself is not the worst part. The worst part is the inescapability of your crewmates. On Earth, even in close relationships, even in small apartments, there is the relief valve of leaving, of walking outside, of having a cup of coffee alone in a park, of experiencing, even briefly, the psychological decompression that comes from being in a large space with other human beings who have no claim on your attention. On Mars, inside the 9-month window, that relief valve does not exist. Your crewmates are always there, their habits, their quirks, their emotional states, their ways of loading the dishwasher and leaving their equipment in the wrong storage bay and humming the same 4 bars of music repeatedly without apparent awareness, all of it is inescapable. And over 9 months, what begins as a personality quirk becomes a psychological irritant. And what begins as a psychological irritant becomes, under sufficient stress and fatigue, a genuine source of interpersonal conflict that can degrade crew function in operationally dangerous ways. NASA's behavioral health researchers use a term for the interpersonal dynamic that tends to develop in isolated, confined crews over long durations. They call it displacement. The crew, unable to direct their frustrations at the environment, which is vast, indifferent, and entirely unhelpful as a target for human anger, begins directing them at each other. The habitat becomes a pressure vessel in the emotional as well as the atmospheric sense. Tension builds, small conflicts take on outsized significance. Grievances that in a normal social environment would dissipate through distance and time instead recirculate endlessly in the closed system of the crew. The research on Antarctic winter-over crews, which represent one of the closest Earth analogues to a Mars surface mission in terms of isolation, duration, and escape impossibility, found that by the midpoint of the winter-over period, the majority of crews had developed at least one significant interpersonal conflict, serious enough to affect operational performance. In some cases, crew members stopped speaking to each other entirely, communicating only through intermediaries or written notes, while continuing to work in physical proximity and shared life support dependency. On Mars, this dynamic would play out under conditions that are, in every relevant way, more extreme. The isolation is more complete, the danger is more real. The stakes of interpersonal failure are higher, and the duration is longer, substantially longer than even the most extended Antarctic winter-over deployments. But the psychological challenges, as serious as they are, exist alongside rather than instead of the physical and mechanical challenges. And those physical and mechanical challenges don't pause while the crew navigates its interpersonal dynamics. They continue relentlessly every day of the 9-month window, demanding attention and correct action regardless of how the humans inside the habitat happen to be feeling about each other on any given morning. The life support system is the most unforgiving of these demands. It is also the most complex, the most interdependent, and the most vulnerable to the kind of cascading failure that begins with a single component fault and escalates through the interconnectedness of the system into a habitat-wide crisis. To understand why, consider water. On the International Space Station, NASA has developed and refined over decades a water recovery system called the Water Recovery System, or WRS, that reclaims approximately 90 to 93% of all moisture entering the system, from urine, from condensation, from exhaled breath, from sweat. This is an extraordinary engineering achievement, one that has been essential to making long-duration human spaceflight economically viable. Without it, the cost of launching sufficient water for a crew's daily needs would be prohibitive. On Mars, the WRS, or its equivalent, will need to perform at even higher recovery rates, 98% or above, because the resupply cadence is not measured in weeks, as it is for the ISS, but in years. A shortfall in water recovery doesn't mean a slightly tighter water ration until the next cargo vehicle arrives. It means a progressive depletion of the water supply over months, with the depletion rate accelerating as the supply shrinks, until a threshold is crossed below which the crew can no longer maintain adequate hydration, and the cascade of physiological consequences begins. Dehydration in the context of a Mars mission is not simply the unpleasant thirstiness of a hot day. Mild chronic dehydration, a consistent deficit of even a few hundred milliliters per day, degrades cognitive performance, impairs judgment, reduces physical endurance, and exacerbates the stress responses that are already being generated by the isolation, the confinement, and the radiation exposure. Moderate dehydration escalates these effects dramatically and begins to compromise kidney function and cardiovascular performance. Severe dehydration, sustained over days, is incompatible with life. The water recovery system, therefore, is not a convenience. It is a survival critical system whose failure timeline is measured not in the seconds or minutes of an explosive decompression emergency, but in the days and weeks of a slow arithmetic depletion that is more insidious because it is gradual enough to be initially deniable and normalized. The oxygen system presents a similar profile. The current state of the art in oxygen generation for long-duration spaceflight involves a technology called electrolysis, the splitting of water molecules into hydrogen and oxygen using electrical power. The oxygen is captured and added to the habitat atmosphere. The hydrogen is typically vented or used in other chemical processes. This system, like the water recovery system, has been operating on the ISS for years, and it works. But it requires power, it requires water, it requires functional electrolysis, hardware, and it requires that the electrical and chemical subsystems that support it remain operational and correctly calibrated. On Mars, the oxygen system will also need to produce oxygen from the Martian atmosphere itself, using a technology that NASA has already begun demonstrating through an instrument called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, which flew on the Perseverance rover and successfully produced small quantities of oxygen from the Martian carbon dioxide atmosphere. Scaled up to crew-sustaining quantities, this technology represents one of the most important enablers of a crewed Mars mission. It means that the crew does not need to carry all of their breathing oxygen from Earth. It means they can, in principle, generate it locally. But it also means they are dependent on a complex chemical engineering process, operating in an extremely harsh environment that must function continuously and reliably for the entire duration of the 9-month window. Any interruption in oxygen generation, any fault in the electrolysis system, any failure in the MOXIE-derived production unit, any sustained power shortfall that forces the system offline begins a countdown of its own. The crew has the oxygen currently in the habitat atmosphere plus whatever is held in emergency reserve tanks. That reserve, depending on the mission architecture, might sustain the crew for anywhere from a few days to a few weeks. Within that time, the fault must be identified, diagnosed, and repaired, with the parts and tools available, by the crew members who are present, without external assistance. This is the operational reality that every technical failure on Mars reduces to. Not how do we fix this, in the comfortable sense of an engineering problem with access to workshops and expertise and time, but how do we fix this right now with what we have before the reserves run out? Power is the master dependency, the resource on which all other survival systems depend. Without power, the water recovery system stops. Without power, the oxygen generation system stops. Without power, the climate control system stops, and the temperature inside the habitat begins migrating toward the Martian ambient temperature, which at night can fall to -80 degrees Celsius. Without power, the communication systems go dark. Without power, the crew's situation transitions from managing a technical fault to managing an existential emergency within hours. Power on a crewed Mars mission will come from one of two primary sources, or more likely, a combination of both. Solar panels are the simpler and more proven technology, the same basic approach that has powered Mars rovers and landers since the Viking missions of the 1970s. But solar power on Mars is subject to a threat that has already claimed the operational lives of two Mars spacecraft: the global dust storm. Mars experiences dust storms on a scale that has no earthly equivalent. Regional storms occur frequently, spanning areas larger than entire Earth continents and lasting for weeks. Global dust storms, events in which the entire planet's atmosphere becomes saturated with suspended dust, occur roughly once every 3 to 4 Martian years, or once every 6 to 7 Earth years. During a global dust storm, the amount of sunlight reaching the surface can drop by 99%. Solar panels, which depend on sunlight, can be reduced to producing 1% of their nominal power output. For a crew depending on solar power, a global dust storm is not an inconvenience to be weathered. It is an extinction event for the mission unless the power architecture has been specifically designed to survive it. The 2018 global dust storm on Mars was the event that ended the Opportunity rover's mission. Opportunity, which had been operating for 14 years on solar power, simply could not generate enough electricity to maintain its battery temperature during the extended darkness, and it never recovered. For a crewed mission, the same scenario, extended dust storm, collapsed solar power generation, rapidly depleting batteries, leads not to a dormant rover waiting for engineers to attempt a wake-up signal, but to a crew in an unheating habitat, watching their oxygen generation system, their water recovery system, and their communication array shut down in sequence as the power reserves drain. This is why nuclear power, specifically a compact fission reactor of the kind NASA has been developing under the kilopower and fission surface power programs, is widely considered essential for a crewed Mars mission. A nuclear reactor produces power continuously, independent of sunlight, immune to dust storms, reliable across the time scales of a Mars surface mission in a way that solar panels simply cannot be. The reactor doesn't care whether it is noon or midnight, whether the sky is clear or choked with suspended iron oxide dust. It produces its rated power output and continues producing it day after day through every dust storm and every Martian winter, and every equipment challenge the crew faces. But a nuclear reactor is also a complex system that must be maintained, that has its own failure modes, and that introduces a set of operational constraints around radiation exposure that must be carefully managed. The reactor cannot be located next to the habitat. It must be positioned far enough away that the crew's radiation dose from reactor operation is kept within acceptable limits. This means power cables running across the Martian surface, exposed to the thermal cycling and dust and micrometeorite environment, representing another set of failure points that must be monitored and maintained. Power, water, oxygen, food, shelter. The 5 pillars of survival on Mars during the 9-month window, each one a complex engineered system, each one dependent on the others, each one subject to failure modes that cascade across the entire survival architecture when they occur. The crew must maintain all 5 simultaneously, every day, for 270 days, with no resupply and no rescue. And they must do this while their bodies are changing, because the physiological effects of the Mars environment do not wait for a convenient moment to manifest. They begin on arrival, some of them before arrival, during the transit, and they progress throughout the 9-month window in ways that are well documented from spaceflight research and deeply sobering when you understand their operational implications. Bone loss is the most widely known. In microgravity and low gravity, the human skeleton begins losing density at a rate that, for the transit phases of the mission, runs at approximately 1 to 2% of bone mass per month. Mars gravity, 38% of Earth's, is better than microgravity for bone maintenance, and the crew will benefit from the daily mechanical loading that walking on the Martian surface provides. But the months of microgravity transit before landing will have already extracted a cost, and the reduced gravity of Mars will not fully arrest the ongoing loss. Over 9 months on the surface, bone density in the weight-bearing skeleton, hips, spine, femurs, will continue to decline. Fractures that would be minor inconveniences on Earth become operationally serious injuries on Mars, where surgical capability is limited. Recovery time is a luxury the mission timeline cannot always afford. And a crew member incapacitated by a broken hip reduces the team's functional capacity by 20 to 25% at exactly the moment that full team capacity is most needed. Muscle atrophy follows a similar trajectory. The reduced gravitational loading of the Martian surface means that muscles accustomed to working against Earth's gravity are perpetually underloaded. Without aggressive, sustained countermeasure exercise, 2 hours per day or more, using resistance equipment that replicates the loading patterns of Earth activity, the muscles of the lower body, the core, and the postural system will shrink and weaken over the 9-month window. And exercise in the context of a Mars mission is not a wellness activity. It is a survival-critical countermeasure that must be maintained with the same rigor as any other life support protocol, even on days when the crew is exhausted, overworked, stressed, and dealing with 3 other simultaneous technical faults. The vision changes are more recently documented and more poorly understood. A condition called spaceflight-associated neuroocular syndrome, SANS, has been observed in a significant proportion of long-duration ISS crew members. It involves a shift in the fluid distribution within the skull, which alters the pressure environment around the optic nerve, causing the nerve to swell and the eyeball itself to change shape in ways that produce vision impairment. The impairment can range from mild near-vision changes to significant degradation of visual acuity. In an environment where reading instrument panels, performing surgical procedures, conducting equipment repairs, and navigating the surface all depend on reliable vision, SANS is not a minor quality of life issue. It is a direct threat to operational capability. And we have not yet talked about the immune system. Spaceflight suppresses immune function in ways that researchers are still working to fully characterize. The mechanisms are multiple: altered stress hormone levels, disrupted sleep, changes in gut microbiome composition, and direct effects of radiation on immune cells all contribute. The practical consequence is that crew members on long-duration missions are more vulnerable to infections, more susceptible to the reactivation of latent viruses that the immune system normally keeps suppressed, and less capable of mounting the robust immune responses that control illness in a healthy person on Earth. On Mars, a routine infection that an Earth-based person would clear in a week with adequate rest, hydration, and immune function becomes a more serious proposition. Medical supplies are finite. The antibiotics, antivirals, and other medications carried on the mission represent a fixed inventory that cannot be replenished. Using medication to treat one illness depletes the supply available for future illnesses. The crew must practice what mission medical planners call consumable stewardship, a careful, rationed approach to medical resources that sometimes means accepting greater short-term suffering in order to preserve the reserve capacity needed for a potential future catastrophe. All of this, the physiological degradation, the psychological stress, the mechanical fragility of the life support systems, the power vulnerability, the communication constraints, is the texture of daily life during the 9-month window. It is not a series of discrete emergencies. It is a continuous, low-level, relentless pressure that exists as the background condition of every waking hour. And it is into this background that the acute emergencies arrive, not instead of the chronic stresses, but on top of them. A medical emergency occurs not on a rested, healthy crew operating well-maintained equipment in a clear sky environment. It occurs on a crew that is 9 weeks into surface operations, somewhat sleep-deprived, mildly stressed by 2 ongoing interpersonal tensions, running their water recovery system at slightly degraded efficiency following a maintenance intervention 3 days ago, and watching a regional dust storm building on the weather sensors that may or may not develop into something more serious. That is the moment when someone's appendix perforates, or a suit seal fails during EVA, or a fire breaks out in the electrical panel of the primary habitat module. That is what the 9-month window actually looks like from the inside. And we are not even halfway through it yet. The dust is rising on the horizon. The clock is still running. And the hardest parts, the parts where the compounding truly begins, where the margin shrinks to nothing, where the decisions that determine whether the crew comes home or stays forever must be made, those parts are still ahead. On Sol 94, the 94th Martian day of surface operations, roughly 3 months into the 9-month window, the dust storm that has been building on the eastern horizon for the past 11 days makes its decision. It expands, not gradually, not incrementally, but with the sudden explosive lateral spread that characterizes the most dangerous class of Martian regional storms, the kind that meteorologists studying Mars from orbit have learned to recognize and dread. Within 48 hours, what began as a localized disturbance over the Hellas Basin, the largest impact crater in the solar system, a depression so vast that its floor sits nearly 8 kilometers below the surrounding terrain, and its atmospheric pressure at the bottom is almost double that of the Martian surface average, has propagated outward in 3 directions simultaneously, drawing energy from the temperature differential between the sunlit dust cloud and the cold Martian surface below, feeding itself, growing. By Sol 96, it covers an area larger than the continental United States. By Sol 103, it has merged with a second storm system developing independently over the Argyre Basin to the west, and the combined system is now tracking toward the crew's landing site with the slow, inexorable momentum of a planetary-scale weather event that has no obligation whatsoever to respect the survival requirements of the 6 human beings directly in its path. The solar panels begin registering the power drop on Sol 97. At first, it is modest, a 10% reduction in output as the first thin veil of suspended dust begins filtering the incoming sunlight. The crew notes it in the daily log, flags it for mission control, and activates the first tier of their power conservation protocol. Non-essential systems go to standby. The lighting in the secondary habitat module is dimmed. The exercise equipment is scheduled for use only during the peak solar window in the Martian midday, when generation is highest. By Sol 100, the power output is down 40%. By Sol 104, it is down 73%. The batteries, the stored energy buffer that allows the habitat to continue operating through the Martian night and through periods of reduced solar generation, are now being drawn down faster than they are being replenished. The charge level that began the storm at 94% is sitting at 61% on Sol 104 morning and dropping at a rate that, if the storm continues at its current intensity and the solar generation continues at its current reduced level, will bring the batteries to the critical 20% threshold, below which the habitat's automatic load-shedding systems begin shutting down non-survival critical systems without crew intervention in approximately 11 days. 11 days. That is the window within the window, the immediate countdown running inside the larger 9-month countdown. This is the operational reality of a Martian dust storm for a solar-powered habitat. It does not threaten you immediately. It threatens you arithmetically. It sets a clock ticking, and then it watches, indifferent, as you work through your power conservation options one by one, and the clock counts down, and the margin shrinks. Mission architects have known about this vulnerability for decades. It is one of the primary arguments for nuclear surface power, for the compact fission reactor that produces its rated output regardless of atmospheric dust loading, that cannot be starved by a storm because it does not depend on sunlight at all. In a mission architecture where the primary habitat power comes from a fission reactor, a dust storm is a serious inconvenience rather than an existential threat. The solar panels on the EVA suit charging system and the secondary equipment go dark, but the reactor keeps the lights on, the oxygen flowing, the water cycling. But in the mission architectures that are most immediately feasible, the ones that rely primarily on solar power with battery storage and limited backup, the dust storm is the scenario that keeps power systems engineers awake. Because the dust storm on Mars is not a rare, extraordinary event. It is a regular feature of the Martian environment, as predictable in its seasonal patterns as hurricane season on Earth's Gulf Coast, and as variable in its severity as any complex weather system embedded in a chaotic atmosphere. Regional storms, covering areas of millions of square kilometers, occur multiple times per Martian year. Global storms, the planet-encircling events that reduce surface solar irradiance by 99%, occur less frequently, but have been observed in 1971, 1977, 1982, 1994, 2001, 2007, and 2018. That is 7 confirmed global storms in roughly 47 years of systematic Mars observation. Statistically, a crewed mission of sufficient duration has a meaningful probability of encountering at least one global storm during its surface stay. The 9-month window places a crew on Mars for approximately 270 Martian solar days, nearly a full Martian year. The probability of encountering at least one significant regional storm during that period approaches certainty. The probability of encountering a storm severe enough to threaten solar power systems is substantial. And yet the dust storm, for all its drama, is not the scenario that Mars mission planners rate as the highest probability cause of mission failure. The dust storm is visible, it is trackable, it develops over days, giving the crew time to respond, to conserve, to prepare. The scenarios that planners lose the most sleep over are the ones that arrive without warning, that have no precursor signals, that demand an immediate response from a crew that may be asleep, or occupied with a separate task, or simply caught in the ordinary inattention of a routine day. The sudden decompression scenario is the paradigmatic example, a micrometeorite, a particle of rock or metal ranging from microscopic to fist-sized, traveling at velocities between 10 and 70 kilometers per second, strikes the habitat. At the lower end of that size range, the result may be a micro-perforation that produces a slow leak detectable by pressure sensors over hours. At the larger end, the result is a structural breach that can produce explosive decompression within seconds. The Martian environment does not have the protective atmosphere that deflects or ablates most of Earth's incoming micrometeorite flux before it reaches the surface. Earth's thick atmosphere vaporizes the vast majority of incoming particles before they reach the ground. Mars's thin atmosphere, less than 1% as dense as Earth's, provides essentially no such protection. Every particle that enters the Martian atmosphere reaches the surface at nearly its original velocity. The probability of a habitat-breaching micrometeorite strike during a 270-day surface mission is low. Mission designers work to minimize it through habitat site selection, through structural shielding, through redundant pressure monitoring. But low probability is not zero probability. And in the context of a mission where a single catastrophic failure can be fatal, low probability events are not dismissible. They are the scenarios for which the crew trains hardest, the ones that drive the design of emergency protocols and rapid response procedures, the ones that populate the nightmares of mission planners who understand that the difference between a successful Mars mission and a tragedy can be a rock the size of a golf ball traveling at 30 kilometers per second. The decompression response protocol, the sequence of actions a crew must execute correctly and rapidly in response to a hull breach, is one of the most intensively practiced procedures in the mission training curriculum. It involves identifying the breach, sealing off the compromised module if possible, donning emergency pressure equipment if the breach is in the primary habitat, and then executing a repair procedure that has to work the first time, because there may not be time for a second attempt. All of this in a crew that may be awakened from sleep by the pressure alarm. In a crew that is 3 months into the surface mission, carrying the accumulated fatigue and stress of 94 sols of high-demand operations. In a crew that is possibly already managing the power conservation protocols of the developing dust storm. In a crew whose hands are already full before the alarm sounds. The compounding of simultaneous stresses is what makes the 9-month window so dangerous and so difficult to simulate accurately. The training scenarios that crews practice on Earth are necessarily sequential, one emergency at a time, with the crew fresh and rested and fully prepared. The real operational environment of a Mars surface mission is not sequential. It is simultaneous and cumulative. The dust storm does not wait for the decompression to be resolved. The interpersonal tension does not pause while the medical emergency is treated. The bone density loss does not stop while the power system fault is diagnosed, and the decisions that must be made in these moments, the real-time, high-stakes, no consultation possible decisions that the crew commander and crew members must execute under stress and time pressure and imperfect information, those decisions are where the human element becomes both the mission's greatest vulnerability and its only real hope. Because the machines, as sophisticated as they are, cannot make decisions. They can execute protocols, they can trigger alarms, they can run automated responses to predefined fault conditions. But when the situation falls outside the predefined parameters, when the failure mode is one that wasn't anticipated in the fault tree, when the combination of simultaneous challenges produces a scenario that the training scenarios didn't cover, when the correct response requires judgment rather than procedure, then it is the humans who must decide. And the quality of those decisions under those conditions in that environment will determine whether the crew comes home. This is why the selection and training of Mars crew members is one of the most consequential human resources decisions in the history of spaceflight. Not because the crew needs to be physically exceptional, though physical resilience matters. Not because they need to be intellectually brilliant, though cognitive capability is essential, but because they need to be psychologically durable in a very specific, very rare way. They need to be the kind of people who, on Sol 104, with the power at 61% and falling, with a dust storm covering half the planet, with a crewmate running a fever that isn't responding to the first-line antibiotic the way it should, with the water recovery system flagging a 2.3% efficiency drop that nobody has diagnosed yet, can sit down, look at all of it simultaneously, prioritize correctly, delegate effectively, communicate clearly, and make decisions that are not perfect, because perfect decisions are rarely available but are good enough, executed well enough to keep everyone alive. The fever matters. Let us stay with the fever for a moment, because the medical dimension of the 9-month window is one of the aspects of Mars mission planning that receives the least public attention and deserves the most. The crew's medical officer, one of the astronauts who has received the most intensive medical training in addition to their primary mission specialty, is monitoring a crewmate who, on Sol 101, reported feeling unwell. Fatigue, mild headache, loss of appetite. By Sol 103, the temperature is 38.7 degrees Celsius. By Sol 104, it is 39.4. The medical officer has access to a well-stocked medical kit, a portable diagnostic suite that can run blood panels and basic imaging, a telemedicine link to a team of physicians on Earth, and a pharmacopoeia of medications selected through years of careful deliberation to cover the most likely and most dangerous medical scenarios a Mars crew might face. They also have on Earth a medical consultation delay of somewhere between 6 and 20 minutes each way, depending on the current Earth-Mars distance. The first diagnostic question is the most important one. Is this a viral infection, a bacterial infection, or something else entirely? The answer determines the treatment. An unnecessary course of antibiotics prescribed for a viral illness that antibiotics cannot affect depletes the antibiotic supply, disrupts the patient's gut microbiome, potentially contributes to antibiotic resistance, and provides no benefit. A bacterial infection left untreated because the medical officer was uncertain of the diagnosis and decided to wait escalates from a manageable illness to a life-threatening systemic infection with a speed that the isolation of Mars makes uniquely dangerous. The portable diagnostic suite provides data. The blood panel shows elevated white cell count, consistent with infection, but not diagnostic of its type. The imaging shows nothing remarkable. The patient's history, their recent activities, their potential exposures inside the habitat, all of this goes into the differential diagnosis that the medical officer constructs and then transmits to Earth, along with the current vital signs and lab values, in a detailed telemedicine consultation request. And then they wait. 6 minutes minimum, likely 12 to 15 given the current orbital geometry, before the first word of response begins arriving from Earth. In that window of waiting, the medical officer must decide whether to begin empirical treatment, treating based on the most likely diagnosis before confirmation, or wait for the Earth team's guidance. If the condition deteriorates rapidly, waiting could allow a treatable infection to advance towards sepsis. If the condition is viral, early antibiotic treatment is wasteful and potentially harmful. This is not a hypothetical dilemma constructed for a thought experiment. It is a real clinical decision that will be faced in some version on a crewed Mars mission. The specific illness will be different. The specific parameters will differ, but the fundamental structure, a sick crew member, limited diagnostic capability, finite medical supplies, delayed consultation, real-time deterioration, will be the same, and it will not be the only medical event of the mission. Over 270 days, a crew of 6 will collectively face a range of medical issues that, statistically, will include dental emergencies, musculoskeletal injuries from EVA activities, gastrointestinal illness, dermatological problems from suit-related pressure and friction, potential cardiovascular events in crew members whose cardiac risk profiles have been shifted by the radiation exposure and physiological stresses of the mission, and psychological crises that may require medical as well as interpersonal intervention. NASA's Human Research Program has spent years developing what it calls the Mars Medical Kit, a carefully curated selection of medications, surgical instruments, diagnostic equipment, and treatment supplies designed to allow the crew's medical officer to manage the full expected range of medical scenarios without resupply. The kit must be comprehensive enough to handle true emergencies, compact enough to fit within the mission's mass and volume constraints, and durable enough to remain functional across the temperature extremes and radiation environment of the Mars transit and surface mission. The surgical capability included in current mission planning is limited but real. A skilled crew member with adequate training can perform certain surgical procedures, wound closure, abscess drainage, appendectomy in some planning scenarios, using the equipment provided. The word appendectomy in that sentence deserves a moment of attention. An appendectomy is a procedure that on Earth is performed by a surgeon in an operating room with a scrub team, anesthesiology support, sterile conditions maintained by a full hospital infrastructure, and the capacity for immediate escalation if complications arise. On Mars, it would be performed by an astronaut whose medical training, however extensive, does not approach the experience level of a surgical resident, in a habitat module that has been converted into an operating space, with a finite supply of anesthetic agents with no capacity for blood transfusion if the patient bleeds more than expected, with the patient being a crewmate whose absence from operations during recovery will stress the entire crew's functional capacity. This is not a reason to conclude that the procedure cannot be performed or that it should not be included in the mission's medical planning. It is performed in remote field settings on Earth, by expedition medics in Antarctica, by military surgeons in austere forward operating bases, with outcomes that, while not equivalent to those achievable in a fully equipped hospital, are nonetheless far better than the outcome of leaving a perforating appendix untreated. The point is not that the procedure is impossible. The point is that it is another example of the margin compression that defines the 9-month window. Every medical scenario on Mars plays out at the edge of what is feasible, with less margin, fewer resources, and higher stakes than the equivalent scenario anywhere on Earth. By Sol 110, the crewmate's fever has broken. The Earth medical team, whose consultation arrived 14 minutes after the initial transmission, concurred with the medical officer's assessment of a likely viral etiology and recommended supportive care, hydration, rest, temperature monitoring, and a 48-hour watchful waiting period before considering antibiotics. The recommendation proved correct. The patient recovers. The antibiotic reserve is intact. But the dust storm is now on Sol 17 of its development, and the power situation has continued to deteriorate. The batteries are at 43%. The power generation from the solar array is running at 19% of nominal. The storm, according to the orbital weather satellite data being relayed through mission control, has not peaked. The meteorological models suggest it may continue at current or greater intensity for another 2 to 3 weeks. The crew has moved through all 3 tiers of their power conservation protocol. Every non-essential system is offline. The habitat is running at minimum viable configuration, life support, communication, navigation, medical, and food preparation systems only. The temperature inside the habitat has been allowed to drop to 16 degrees Celsius to reduce the thermal management load on the power system. The crew is wearing additional layers. The exercise protocol has been suspended, not because exercise is unimportant, but because the power draw of the resistance equipment is a luxury the system can no longer support, and the batteries are still dropping. At the current rate, the critical 20% threshold will be reached in approximately 8 days. Below 20%, the habitat's automated systems will begin shutting down loads in a predetermined priority sequence. The last systems to be shut down are the oxygen generation and the minimum heating required to prevent equipment damage from cold. Before it reaches those last shutdowns, the system will have already sacrificed communication, the water recovery system's active filtration pumps, the medical diagnostic equipment, and the food preparation systems. The crew has one option remaining that mission planners built into the architecture precisely for this scenario. The backup power module, a compact secondary system that can be deployed from storage and connected to the habitat power bus, is designed to provide approximately 30% of nominal power capacity from a combination of stored fuel cells and a small secondary solar array with more efficient but more fragile panels. Deploying it requires an EVA, a suited surface excursion, during which a crew member must spend approximately 4 hours outside the habitat in a dust storm that is reducing visibility to less than 50 meters, connecting the backup module's power conduits to the habitat's external power interface. The dust storm makes the EVA dangerous. The suit's solar-charged batteries will drain faster than normal in the reduced light. The dust will infiltrate the suit's joints and seals in ways that are not immediately damaging, but accumulate into degraded suit performance over subsequent EVAs. The visibility limitations increase the navigation risk. A crew member who loses orientation in a low visibility dust storm and wanders beyond the habitat's immediate perimeter is in immediate danger from the environment. But the alternative, waiting for the storm to clear while the batteries continue to drop, carries its own escalating risk. If the batteries reach the automated load-shedding threshold before the storm breaks, the crew loses control of the sequence in which systems shut down. The automated system will follow its priority list, and the priority list was written before the mission launched by engineers who could not know the specific configuration of vulnerabilities that would exist on Sol 118 of this specific mission. The crew commander makes the decision. The EVA goes forward. 2 crew members suit up, primary and backup, the standard EVA pairing. The airlock cycles. The outer door opens onto a sky the color of a bruise, thick with suspended iron oxide particles that scatter what little light penetrates the dust cloud into a flat, directionless, rust-colored murk. Visibility is approximately 35 meters. The habitat's exterior lights create halos in the dust, not illumination. The 2 suited figures move methodically along the safety line that runs from the airlock to the backup power module's storage bay, a line that exists precisely for this scenario, a physical tether to the habitat in conditions where visual navigation would be unreliable. The connection procedure takes 3 hours and 40 minutes, One connector proves difficult, a dust accumulation in the coupling interface that requires careful manual clearing before the connection will seat properly. The crew members' gloved hands work slowly and precisely, the gloves providing dexterity protection against the minus 60-degree ambient temperature, but reducing tactile feedback to a fraction of what bare hands would provide. The suit's internal temperature is comfortable. The suit's internal atmosphere is clean. Outside the suit, the environment is instantly lethal. The connection seats. The power bus indicator in both crew members' suit displays shows green. They begin the return traverse along the safety line. Back inside, the airlock cycling behind them, the dust decontamination protocol beginning, the careful, practiced sequence of brushing and vacuuming that removes as much perchlorate-laden dust from the suits as possible before they are removed and the crew members re-enter the habitat's clean atmosphere. The power display on the habitat management console shows the backup module coming online. The battery charge level, which has been ticking downward for 11 days, stabilizes. Then, very slowly, it begins to rise. 43%, 44, 45. The crew commander allows herself one moment of something that is not quite relief. Relief is premature. The storm is still raging, the main power system is still degraded, the medical recovery is still incomplete. The water recovery efficiency drop is still undiagnosed, but is perhaps its structural precursor. The immediate crisis has been managed. The margin has been rebuilt, slightly, from the dangerous edge it was approaching. The clock is still running. They are on Sol 119 of 270. They have 151 days remaining before the return window opens, and they are more tired than they have ever been in their lives. There is a specific kind of exhaustion that has no good name in ordinary language. It is not the exhaustion of a hard day's work, which carries within it a satisfying heaviness, the body's honest accounting of effort, expended toward a completed purpose. It is not the exhaustion of illness, which at least offers the clarity of a defined cause and the reasonable expectation of recovery. It is the exhaustion of sustained vigilance, of weeks and months spent in a state of continuous low-level alertness, in which the normal human capacity to relax, to truly disengage from responsibility, to sleep without one part of the mind remaining on watch, has been so thoroughly suppressed by circumstance that it begins to feel like a faculty that no longer exists. Astronauts on the International Space Station describe it. Antarctic winter-over researchers describe it. Submariners on extended deployments describe it. And every one of them, when asked to characterize what it actually feels like from the inside, reaches for the same metaphor in slightly different words. It feels, they say, like the background noise of the environment has gotten inside you, like the hum of the machinery, the recycled air, the artificial light cycling on its programmed schedule, the constant soft presence of systems that are always running and always need watching. Like all of it, has migrated from outside the body to inside it, and now runs there too, a second metabolism, a parallel system of monitoring and maintenance that operates alongside the biological one and draws from the same finite reserve of energy. On Sol 127, 8 days after the backup power module EVA, the dust storm begins to weaken. The degradation is initially imperceptible to anything other than instruments. The solar panels register a 2% improvement in generation efficiency on the morning of Sol 127. By afternoon it is 4% above the storm baseline. By Sol 130 it is 11% above baseline, still far below nominal but moving in the right direction with a consistency that suggests the storm is genuinely retreating rather than temporarily fluctuating. By Sol 138, the generation is at 67% of nominal and climbing. The storm has lasted 41 Martian days, nearly 7 Earth weeks. It is the longest sustained power challenge the crew has faced, and it has extracted costs that will not be fully visible for some time. The physical costs are the most easily measured. The suspended exercise protocol means 6 weeks of reduced countermeasure activity at a phase of the mission when the cumulative effects of reduced gravity on bone and muscle are already advancing. The muscle mass losses that the exercise protocol was designed to prevent have accelerated. The bone density scans that the medical officer runs on Sol 140, once the power situation has stabilized sufficiently to bring the diagnostic equipment back online, show measurable additional loss in 3 of the 6 crew members beyond what the pre-storm trajectory had predicted. Not catastrophic, not injury threshold loss, not immediately dangerous, but a deduction from the biological reserve that cannot be reversed on Mars and will need to be carefully managed during the return transit and the post-mission recovery on Earth. The water recovery system's efficiency deficit, which had been sitting at 2.3% below nominal since Sol 96 and had not been diagnosed before the storm consumed all available engineering attention, turns out on inspection to be a partially clogged filtration membrane in the primary processing loop. The repair is straightforward once the fault is correctly identified. A membrane replacement from the spare parts inventory, a 45-minute procedure that 2 crew members complete on Sol 141 with a thoroughness that reflects both the technical clarity of the task and the particular psychological relief of having a problem that can be definitively fixed. The water recovery efficiency returns to 97.8% of nominal after the repair. The water reserve, which had been very slowly declining during the storm period due to the combined effects of the efficiency drop and the reduced recycling cycle that came with power conservation, begins recovering. But the psychological costs of the storm period are less easily measured and slower to resolve than the physical ones. They do not repair themselves through a membrane replacement or a charging cycle. They sit in the crew's interpersonal fabric like a slow stain, visible in the quality of conversations, in the latency between statements and responses, in the slightly elevated frequency of small frictions that have no real cause except the accumulated pressure of 7 weeks of sustained crisis management in a space the size of a large recreational vehicle. The crew is on Sol 143. They have 127 days remaining before the return window opens. There is a concept in organizational psychology called psychological safety, the degree to which members of a team feel able to speak honestly, acknowledge uncertainty, surface concerns, and admit mistakes without fear of judgment or reprisal. It is one of the most robustly supported predictors of team performance across domains ranging from surgical teams to software development groups to military units. Teams with high psychological safety make better decisions, catch more errors before they become consequential, and recover more effectively from setbacks. Teams with low psychological safety suppress information, hide uncertainty, and compound errors through the fear of admission. On a Mars surface crew, psychological safety is not a soft organizational metric. It is a survival variable. A crew member who is afraid to say, "I'm not sure I understood that procedure correctly," or "I think I may have made an error in that calculation," or "I'm not okay right now and I need someone to know that." That crew member is a source of operational risk that cannot be corrected by any technical system. The habitat's fault detection software cannot detect human self-concealment. The mission's automated monitoring systems cannot flag the moment when someone stops saying what they are actually experiencing. The research on crew dynamics in isolated, confined environments is consistent on this point. The single most effective predictor of whether a crew maintains psychological safety over a long-duration mission is the quality and consistency of crew communication practices. Specifically, the degree to which the crew has internalized structured communication habits that create regular, low-stakes opportunities for honest disclosure, and the degree to which the crew commander models the kind of vulnerable, honest self-disclosure that gives permission to others to do the same. It sounds almost simple when stated that way. Talk to each other. Be honest about what you are experiencing. Create the conditions under which problems can be named before they become crises. In practice, on Sol 143 of a Mars surface mission with 127 days remaining after 7 weeks of dust storm crisis management, after a medical emergency, after an EVA in near-zero visibility conditions, after 6 weeks of suspended exercise and accumulating physiological deficits, after months of breathing recycled air and sleeping in artificial light and eating food from packages, in practice, on that specific morning, in that specific crew, it requires something closer to heroism than to simple communication. Because everything in the environment militates against it. The exhaustion makes honesty feel like an additional expenditure of energy that the system can barely afford. The confinement makes vulnerability feel dangerous. If you disclose that you are struggling, you cannot leave the room afterward, cannot create distance, cannot allow the disclosure to settle and be processed in privacy. The stakes make the appearance of competence feel like a survival necessity. If you are the person who admitted uncertainty at a critical moment and then the critical moment went wrong, the causal chain feels unbearably direct in a way that it never would in a more forgiving environment. The crew commander on Sol 143 calls a structured crew meeting, not a technical briefing, not an operational planning session, but the kind of meeting that the behavioral health protocols built into the mission plan call for at regular intervals, a check-in focused specifically on how the crew members are doing as human beings rather than as operational assets. The protocols exist because the research is clear. Without a structured mechanism that makes the check-in a normal, expected, non-optional part of the mission rhythm, the check-in does not happen. Individual crew members assume that everyone else is managing better than they are. The assumption of others' competence becomes a barrier to the disclosure of one's own difficulty. The crew becomes a collection of individually struggling people, none of whom knows that the others are also struggling, all of whom are expending energy on the performance of coping that would be better spent on actual coping. The meeting takes 90 minutes. What is said in it will not be reconstructed here because the specific content belongs to the crew and to the therapeutic relationship between the crew and the behavioral health support team on Earth that will review the meeting log. But what emerges from it, the operational consequence, the thing that changes as a result, is a recalibration of the workload distribution that has developed organically over the storm period and has quietly, without anyone planning it, placed a disproportionate burden on 2 of the 6 crew members. Those 2 crew members have been carrying operational loads that exceed what the mission plan intended, have been masking the excess load through efficiency and self-reliance, and have been accumulating a fatigue debt that is now visible to anyone looking carefully at their performance, metrics, reaction times, decision latency, error frequency in procedural tasks, even if it has not been visible to the crew members themselves. The recalibration takes 3 days to implement. Workload is redistributed. Sleep schedules are adjusted. 2 crew members are placed on a reduced operations schedule for 72 hours, not removed from duty, because the mission cannot afford the full absence of any crew member, but given a deliberately lighter load that allows some partial recovery of the fatigue debt without abandoning the operational continuity the mission requires. On Sol 148, the first full Martian day after the recalibration is complete, the error rate in procedural tasks drops by 34% compared to the storm period average. This is not a statistic that anyone celebrates openly, because celebrating it would require acknowledging how degraded performance had become during the storm period, and that acknowledgement carries its own weight. But it is noticed. It is logged, and it becomes one of the most valuable data points the mission will produce. Not about Mars, not about life support systems or radiation shielding or orbital mechanics, but about the human beings inside the mission, about the cost of sustained stress, about the measurable, quantifiable, operationally significant difference between a crew that is coping and a crew that is performing. They are on Sol 148. They have 122 days remaining before the return window opens. The dust storm is over. The power systems are recovering. The water recovery system is repaired. The sick crew member is fully recovered and back on full duty. The workload has been recalibrated. The crew is, relative to where it was 3 weeks ago, in a better position. And it is precisely at this moment of relative stabilization, of cautious optimism, of the first suggestion that the worst might be behind them, that the mission encounters the failure mode that was not in any training scenario, the one that did not appear in the fault tree, the one for which the procedures manual has no specific entry, because no one anticipated this exact combination of circumstances, and no combination of circumstances is ever exactly anticipated. On Sol 151, the primary navigation computer, the system responsible for calculating EVA routes, tracking crew member positions during surface excursions, managing the autonomous systems that monitor the habitat's external environment, and maintaining the precise orbital and positional calculations that the return launch will require, begins producing anomalous outputs. The anomaly is subtle at first, a positioning calculation for an EVA waypoint that places the waypoint 3.7 meters from its surveyed location. A thermal imaging scan of the habitat exterior that shows a temperature gradient inconsistent with the current ambient conditions. An orbital mechanics calculation for a routine communication window that is off by 0.003 degrees of antenna, pointing angle, small enough to be within the system's stated tolerance, but wrong in a specific direction that suggests a systematic rather than random error. The crew's systems engineer, the crew member with primary responsibility for the habitat's computer and navigation systems, identifies the pattern on Sol 152 when a fourth anomalous output appears that shares the same systematic bias as the previous 3. This is not random sensor noise, this is a coherent error, a consistent directional deviation in a specific class of calculations that suggests something is wrong, not with individual sensor inputs, but with a computational process that underlies multiple system functions. The systems engineer's first hypothesis is radiation damage. The navigation computer's processors, like all electronics on a Mars mission, are exposed to galactic cosmic rays and solar energetic particles throughout the mission. High-energy particles passing through semiconductor devices can flip individual bits in memory, corrupting stored data, or altering the state of computational logic elements in ways that range from trivially self-correcting to catastrophically persistent. The accumulated radiation dose on Sol 151 is consistent with a meaningful probability of bit flip errors in unshielded memory elements. The computer's error correction systems are designed to detect and correct single-bit errors automatically, but they are not perfect, and a specific class of multi-bit error can sometimes evade detection while producing exactly the kind of systematic bias that the systems engineer is now observing. The diagnosis matters enormously because it determines the repair approach. If the problem is a radiation-induced bit error in a specific memory location, the fix may be as simple as identifying the corrupted memory address, restoring the correct value from a backup, and running a comprehensive memory diagnostic to find and correct any additional corrupted locations. If the problem is hardware damage to a processing element, a transistor junction permanently altered by a high-energy particle strike, the software fix will not work, and the repair options depend entirely on whether the damaged component can be identified, isolated, and bypassed or replaced using the spare hardware inventory. The systems engineer begins the diagnostic sequence on Sol 152. It is a process that the training simulations estimated would take approximately 18 hours. On Sol 152, 153, and 154, 54 hours of intensive diagnostic work, conducted while the rest of the crew maintains habitat operations and manages the ongoing demands of the mission. The systems engineer works through the diagnostic tree with a methodical thoroughness that the post-mission analysts will later describe as exemplary. The problem, when it is finally localized on the morning of Sol 155, is not radiation damage. It is something more mundane and in some ways more troubling. A firmware update that was transmitted from Earth on Sol 89 and during the pre-storm period, when the crew's attention was focused on storm preparation and the update was installed by an automated process without manual review, contained a single-line error in a subroutine used for coordinate transformation calculations. The error was not present in the version of the firmware that was tested on Earth before transmission. It was introduced during the transmission compression process, a 1-bit corruption in the transmitted data that the transmission error correction system failed to catch, that installed itself silently into the navigation computer's firmware, and that has been producing systematically biased outputs in every calculation involving the affected subroutine ever since. For 62 sols, the navigation computer has been wrong. Subtly wrong within the system's stated tolerances for most outputs, but wrong in a consistent direction that has been influencing EVA route calculations, habitat external monitoring, and most critically, the preliminary return launch trajectory calculations that the crew's flight engineer has been running as preparatory work for the return window now 115 days away. The return trajectory calculations are wrong. Not dramatically wrong, not wrong in a way that would have sent a return vehicle careening off into interplanetary space on an unrecoverable trajectory, but wrong in a way that, if not corrected before the return launch, would produce a transit arc that misses the Earth arrival corridor by a margin sufficient to require additional propellant for correction. Propellant that the return vehicle may or may not have available in sufficient quantity, depending on the amount of correction needed. The clean fix is straightforward once the corrupted firmware line is identified. Restore the correct firmware from the pre-transmission backup, which is stored in the mission's archives, and rerun all calculations performed since Sol 89 using the corrected system. The systems engineer and the flight engineer spend Sol 156 and Sol 157 doing exactly this. Earth is notified. The 14-minute response confirms the diagnosis and validates the repair approach, and by the end of Sol 157, the navigation computer is running the correct firmware and producing validated outputs. The rerun return trajectory calculations are completed on Sol 158. The corrected trajectory is within the expected parameters. The return launch window is confirmed. The propellant budget is adequate. But Sol 158 is also the day when the crew learns from a medical scan that the crew's medical officer has been tracking with increasing concern over the previous 3 weeks, that one of the crew members has developed a finding that requires a difficult conversation. The finding is a growth, a small, abnormal tissue mass in the abdominal cavity, detected on the portable ultrasound imaging system and confirmed by the CT equivalent scanning capability that the mission's medical kit includes for exactly this kind of diagnostic need. It is approximately 1.4 centimeters in diameter. It was not present or not detectable at this imaging resolution on the pre-mission medical clearance scans performed on Earth before departure. What it is precisely cannot be determined with the diagnostic capability available on Mars. It could be benign, a cyst, a lipoma, a reactive lymph node from the earlier viral illness. It could be something more serious. The radiation environment of the mission, or the elevated galactic cosmic ray exposure, the solar energetic particle events, the accumulated dose that has been building since departure, is a known risk factor for exactly the kinds of cellular DNA damage that can initiate malignant transformation. The statistical probability of a radiation-induced malignancy developing and becoming detectable within the time frame of the mission is low, but the statistical probability of the finding being benign is also not certainty. It is probability. And in the 9-month window on Sol 158, with 112 days remaining, probability is the only currency available. The medical consultation with Earth, the detailed transmission of imaging data, laboratory values, and clinical findings, followed by the 14-minute wait, followed by the response from the oncology and radiology consultants assembled by the Earth medical team, takes most of Sol 159 to complete. The Earth team's assessment when it arrives is measured and careful and honest about its limitations. The imaging characteristics are more consistent with a benign process than a malignant one. The most likely diagnosis, given the clinical context, is a reactive lymph node or a benign cyst related to the prior viral illness. But definitive diagnosis requires tissue sampling and pathological analysis, which cannot be performed on Mars. Watchful waiting, serial imaging at regular intervals, monitoring for growth or change in characteristics, is the recommended approach. Return to Earth for definitive evaluation as soon as possible after mission completion. The crew member receives this information with a composure that those who know them will later describe as characteristic. They ask 3 clinical questions of the medical officer. They read the Earth team's consultation document twice. They go to their bunk for 40 minutes. Then they return to their duty station and resume their scheduled tasks for the day. On Sol 160, the crew is 110 days from the return window. They are physically depleted. They are carrying an unresolved medical uncertainty that no amount of careful monitoring can resolve before they leave Mars. They have lived through a 7-week dust storm, a medical emergency, a navigation computer fault, and the accumulated psychological weight of 5 months of sustained high-stakes operations in one of the most hostile environments in the solar system. And they are, by every operational metric available, still functioning, still making correct decisions, still maintaining the life support systems, the scientific research program, the communication schedule, the interpersonal fabric of the crew, still doing the work. Because that is what the 9-month window ultimately demands, not heroism in any cinematic sense. Not a single moment of transcendent courage that resolves the crisis and saves the mission, but the grinding, day after day, decision after decision, maintenance and repair and communication and adaptation. That is what survival actually looks like when the extraordinary has been stripped of its glamour and reduced to its operational core. 110 days. The clock is still running. The return window is approaching, still distant, still not guaranteed, but approaching with the same patient orbital arithmetic that set the 9-month window in motion in the first place. The planets are moving. The geometry is changing. The exit is coming. Whether the crew reaches it, in what condition, with what reserves, with what they have learned, and what they have lost, and what they carry back with them into the world they left behind 9 months ago. That is what the final part of this story will tell. On Sol 220, 70 days before the return window opens, the crew conducts what mission planners call the point of no return assessment. It is not a dramatic ceremony. There is no formal announcement, no moment of collective pause in which the crew gathers to mark the occasion. It is a technical review, a systematic evaluation of every survival critical variable against the mission's go/no-go criteria for the return launch. Life support system status, propellant reserves, crew medical status, navigation system validation, habitat integrity, power system health, communications readiness. Each variable is assessed, documented, and compared against the minimum acceptable threshold for a successful return. The point of no return assessment exists because there is, embedded within the larger 9-month window, a smaller inner window. A specific period during which a crew facing an unrecoverable life support failure or a catastrophic medical emergency might, under certain conditions and with sufficient propellant reserves, execute an emergency early return. The orbital mechanics that make Mars return launches possible only during specific windows also define this inner window, and it is narrow. Perhaps 2 to 3 weeks in duration, depending on the specific mission architecture and the orbital geometry of the particular launch year. Before this inner window closes, an emergency early departure is theoretically possible, at the cost of using propellant reserves that would normally be held for contingencies during the return transit. After it closes, the crew is committed. Whatever happens next, they are staying on Mars until the primary return window opens. Sol 220 is the last day of that inner emergency return window. The assessment takes 4 hours. The crew's commander and flight engineer run the calculations while the rest of the crew continues normal operations. The results are documented in a report that is transmitted to Earth and will later become one of the most studied documents in the history of crewed spaceflight, not because of what it reveals about the technology, but because of what it reveals about the human capacity to persist through accumulated adversity and arrive at a moment of genuine, earned readiness. Every variable passes, not comfortably, not with the generous margins that the pre-mission planning documents had optimistically projected. The propellant reserves are at 94% of the return launch requirement, adequate, but carrying less margin than the planned 105% that would have provided full contingency coverage. The water recovery system is operating at 97.8% efficiency, functional but requiring weekly maintenance attention that the pre-mission planning had assumed would be monthly. 3 crew members are carrying bone density deficits that exceed the pre-mission projections, requiring a modified exercise protocol during the return transit and an extended rehabilitation program after Earth return. The unresolved medical finding in 1 crew member remains stable on serial imaging. No growth, no change in characteristics, consistent with the benign assessment, but unresolved, a persistent uncertainty that the crew has learned to carry without allowing it to dominate the operational foreground. Everything passes. The inner emergency return window closes. The crew is committed, and something shifts. It is difficult to characterize precisely, but every long-duration spaceflight crew that has passed a genuine point of no return describes a version of the same shift. The anxiety that comes from optionality, from the knowledge that departure is theoretically possible, that the decision to stay has not yet been irrevocably made, that anxiety resolves. Not into comfort, not into relaxation, but into something that is in some ways more functional. A clarity, a narrowing of the decision space that paradoxically makes decisions easier rather than harder. The question is no longer whether to stay. The question is simply how to do what must be done for the time that remains, as well as it can possibly be done. 70 days. In the architecture of the 9-month window, the final 70 days before the return launch are operationally the most intensive and logistically the most complex. The crew is simultaneously maintaining all the survival systems that have sustained them for the previous 220 sols, conducting the final phase of their scientific research program, beginning the systematic process of packing and preparing equipment and samples for return, and running the increasingly detailed preparatory work for the return launch itself. The trajectory calculations, the vehicle systems checks, the abort scenario planning, the communication protocol verification with Earth. The science in the context of everything else deserves more attention than it typically receives in discussions of Mars mission survival. Because the survival framing, the 9-month window, the ticking clock, the compounding risks, can create the misleading impression that a crewed Mars mission is purely a survival exercise, that the scientific research is a secondary objective that gets done when everything else permits. This framing is both understandable and wrong. The scientific work is not secondary. It is, in the most fundamental sense, the reason for doing all of this at all. Human beings are going to Mars, not robots, not instruments, not autonomous systems, but fragile, expensive, irreplaceable human beings, because there are questions about Mars that robots cannot answer. Questions about the detailed geology of specific sites, examined with the pattern recognition and contextual understanding that a trained geologist brings to a rock face in a way that a robotic arm and a spectrometer simply cannot replicate. Questions about the subsurface environment explored through drilling and sampling operations that require the real-time adaptive judgment of a scientist physically present at the location. Questions about the potential for past or present life. Biological questions whose answers may depend on recognizing subtle patterns in texture, chemistry, and spatial distribution that the human visual and cognitive system is, for now, uniquely capable of detecting. On Sol 231, 11 days after the point of no return assessment, the crew's geologist and astrobiologist are conducting what will become the most discussed EVA of the mission, a 6-hour surface excursion to an outcrop of layered sedimentary rock approximately 2.3 kilometers from the habitat that orbital imaging had flagged as a high-priority target before the mission launched and that the crew has been planning to investigate for the past 40 days. The outcrop is in a shallow valley, a feature that, on Mars, is significant because valleys accumulate sediment, and sediment is where the record of past environmental conditions is most legibly preserved. The layers exposed in the valley wall represent, according to the pre-mission geological analysis, a sequence of deposition that spans perhaps hundreds of millions of years of Martian history, a compressed archive of climate, chemistry, and potentially biology, covering a time span that dwarfs the entire history of complex life on Earth. The geologist works through the lower layers systematically, collecting samples, photographing contacts, noting the subtle variations in color and texture and grain size that tell the trained eye about the conditions under which each layer was deposited. The work is slow and careful. EVA time is precious. Each hour outside the habitat costs suit, consumables, crew fatigue, and operational risk, and the geologist is not going to rush a rock face that has been waiting to be examined for approximately 3.5 billion years. In the third hour of the EVA, at a depth in the section that the geologist's field mapping places at roughly 2.1 billion years before present, a layer approximately 8 centimeters thick catches the light at an angle that produces a visual texture unlike anything in the layers above or below it. The geologist pauses, leans closer. The texture is fine and regular, too regular for purely physical processes, with a spatial periodicity that, in the geologist's experience of terrestrial rocks, is associated with biological mat structures, microbial mats. The kind of thin films of microorganisms that colonized shallow marine environments on early Earth and left their physical imprint in the sedimentary record as the characteristic laminated structures that geologists call stromatolites. The geologist does not say anything dramatic, they say, with the careful precision of someone who knows that extraordinary claims require extraordinary evidence and that this moment, whatever it turns out to be, will be examined by every scientist on Earth for years to come. I need the camera over here. I am looking at something I want to document very carefully before I say anything else about it. The astrobiologist moves to the location. They look at the structure together. They photograph it from multiple angles, in multiple lighting conditions, at multiple magnifications. They collect 4 samples, 2 from within the structure, 2 from the layers immediately above and below, for comparative analysis. They note the GPS coordinates, the precise depth in the stratigraphic section, the aspect and dip of the layer, the spatial extent of the feature. They do not conclude anything. They cannot. The samples will need to be analyzed with equipment far more sophisticated than what the mission carries by laboratories on Earth over months of careful investigation. The feature could be biological, it could be abiotic. There are geological processes capable of producing regular, laminated textures without biological involvement, and until those possibilities have been rigorously excluded, no conclusion is warranted. But the geologist and the astrobiologist both know what they are looking at. They have both spent their professional careers studying exactly this kind of evidence in terrestrial rocks and in meteorites, and in the theoretical frameworks that predict what biological signatures might look like in the Martian sedimentary record. And they both know that this texture, in this context, in this layer of this age, is the most important thing that has happened in the history of Mars exploration. They complete the EVA, they cycle through the airlock, they go through decontamination, they secure the samples in the designated containers, and then the geologist sits down at the communications terminal and begins composing the transmission to Earth that will, after a 16-minute transit, after a 16-minute response lag, after the mission control scientists on the other end have had their own moment of looking at the transmitted images with the particular stillness of people confronting something that may change everything, begin one of the longest and most carefully conducted scientific conversations in human history. The samples are going home. Whatever they contain, whatever the answer turns out to be, is coming back to Earth in the return vehicle with the crew. The most precious cargo in the history of space exploration, packed in sealed containers, stored in the sample return vault, waiting for the 70 days to pass. Sol 240. 60 days remaining. The return vehicle pre-launch checks begin in earnest. The ascent vehicle, the spacecraft that will lift the crew off the Martian surface and into the elliptical orbit, where it will rendezvous with the Earth return vehicle waiting in orbit, has been sitting on the landing pad adjacent to the habitat since before the crew arrived, pre-positioned by a previous uncrewed mission to ensure that it was fueled and functional before any human beings committed to the surface. It has been sitting in the Martian environment for approximately 26 months, exposed to the temperature cycling, the radiation, the dust, and the periodic wind loading of a planet that has had nearly 2.5 years to work on it. The vehicle checks are methodical and comprehensive. Every system is tested, verified, and documented. The propellant loading is confirmed. The navigation and guidance systems, now running on the corrected firmware installed after the Sol 151 anomaly, are validated against multiple independent reference sources. The communication systems are checked on all frequencies. The life support systems for the ascent phase are tested and confirmed. The abort scenarios are reviewed and rehearsed. On Sol 247, the checks find a fault. A seal in the primary propellant feed line, one of the connections between the propellant tank and the engine feed system, shows a pressure test result 3.2% below the acceptable threshold. Not dramatically below, not immediately catastrophic, but below the threshold that the pre-launch checklist defines as acceptable for launch commitment, in a component whose failure during ascent would result in loss of thrust at the worst possible moment during the powered ascent phase, when the vehicle is climbing through the thin Martian atmosphere on a trajectory that allows no margin for engine underperformance. The seal replacement procedure exists in the maintenance manual. It is documented, it has been trained, and the required replacement seal is in the spare parts inventory. But accessing the seal requires partially disassembling a section of the propellant feed system in a way that, in the Martian environment, carries its own risks. The disassembly must be performed in a suit. The components involved are small enough that the reduced tactile sensitivity of pressurized gloves makes the work genuinely difficult. And the propellant lines, once disturbed, must be carefully purged and recommissioned in a sequence that the maintenance manual describes as requiring a minimum of 18 hours from beginning to end. The crew has 53 days before the return window opens. They have abundant time for the repair. The 18-hour timeline is not a constraint. What is a constraint is the weather. A regional dust storm, smaller than the monster of Sol's 97 through 138 but significant, is developing to the east, and the meteorological data suggests it will pass over the landing site within approximately 36 hours. Working on the propellant system during a dust storm is not impossible, but it introduces contamination risks that the maintenance manual explicitly flags as requiring enhanced precautions, slowing the procedure and increasing the probability of a secondary fault during recommissioning. The crew commander makes the decision to begin the repair immediately to complete as much of the procedure as possible before the storm arrives, and to time the most contamination-sensitive steps for the period after the storm passes. The systems engineer and the flight engineer begin suit-up at 0600 on Sol 248. By 1400, the propellant feed line has been partially disassembled, the faulty seal has been removed and confirmed as the source of the pressure deficit. A hairline crack in the elastomer material, almost certainly a thermal fatigue failure from 26 months of Martian temperature cycling, and the replacement seal has been installed. The storm arrives at 1730. The recommissioning sequence is suspended. The partially reassembled feed line is secured in a protective configuration designed to minimize dust infiltration during the storm. The crew returns to the habitat. The storm lasts 31 hours. On Sol 250, the recommissioning sequence resumes. By Sol 251 morning, the propellant feed line is fully reassembled, the purge sequence is complete, and the pressure test shows 99.7% of nominal, well above the acceptable threshold within the system's normal operating range. The ascent vehicle is cleared for launch. Sol 251. 49 days remaining. The final weeks pass with the particular quality of time that belongs to endings. The scientific work continues, but with a completeness to it that the earlier phases of the mission lacked, the sense of a chapter being brought to its close rather than a chapter in the middle of being written. The crew conducts final sampling runs at the sites that have yielded the most interesting data. The geological samples are catalogued, documented, and sealed. The atmospheric data collected throughout the mission is compiled and formatted for transmission. The biological monitoring data, the physiological measurements, the psychological assessments, the medical records, is organized for the Earth research teams who will spend years analyzing it. The habitat systems are maintained at full operational standard until the final week. There is no coasting, no relaxation of the maintenance protocols because the end is approaching. A habitat that degrades in its final weeks can still kill the crew in its final days. The life support systems receive the same level of attention on Sol 260 that they received on Sol 10. This is discipline in its purest form, not the discipline of motivation or enthusiasm, but the discipline of understanding deeply and completely what happens when the discipline lapses. The crew member with the unresolved medical finding receives a final imaging assessment on Sol 255. The finding is unchanged. Same size, same characteristics, no features suggesting malignant transformation. The Earth medical team's assessment remains consistent with a benign process. The finding will be evaluated definitively within days of Earth return, when the crew member has access to a full surgical and pathological workup. The uncertainty that has been carried for 97 days will be resolved. Not here, not now, not on Mars, but soon. On Sol 261, the crew conducts the final habitat shutdown sequence. The systems that are not needed for the final 9 days of pre-launch preparation are powered down in a sequence designed to preserve the habitat in a stable configuration for as long as possible. Not because anyone is planning to return to it, but because the habits of operational care are not abandoned simply because departure is imminent. The habitat may be visited by future missions. The equipment left behind may be useful to crews who come later. Everything is secured, documented, catalogued, and left in as good a condition as the 9 months of use permit. On Sol 265, the crew performs their final EVA. It is not scheduled as a final EVA, it is a routine equipment check of the ascent vehicle's exterior systems, confirming that no dust accumulation has blocked any vents or sensor ports since the most recent check 4 days ago. But it becomes in the way that final things often become what they are through the quality of attention brought to them, something more than routine. The geologist pauses on the return traverse from the ascent vehicle to the habitat and turns to look at the landscape. The particular landscape of this particular place, the low hills in the middle distance the colour of old rust and pale ochre, the sky above them a shade of butterscotch that is specific to late afternoon in this season at this latitude, the shadows long and precise in the thin atmosphere that scatters light differently than Earth's air and produces a quality of illumination that has no name in any Earth language because no human being had ever seen it before this crew arrived. The geologist stands there for 47 seconds. This is logged. The EVA position tracking system records the pause as an anomaly and flags it in the daily operations log, where it will later be reviewed and noted, with the dry precision of mission documentation as a non-operational pause of 47 seconds at waypoint 7 of EVA 94, attributed to crew member observation. 47 seconds of looking at Mars, of being, perhaps, the last human being to stand in this precise location and look at this precise view for decades or centuries to come, of holding, in whatever way a human mind holds such things, the full weight of where they are and what they have done and what they are leaving behind. Then the geologist turns and walks back to the airlock. Sol 270, launch day. The ascent vehicle ignites at 08:47 local time, chosen for the specific orbital mechanics of the rendezvous with the Earth return vehicle waiting in Mars orbit. The thrust is immediate and clean, the repaired propellant feed line performing exactly as the pressure tests predicted, the engine producing its rated thrust within 0.3%. The vehicle climbing through the thin Martian atmosphere on the precise trajectory that the corrected navigation system calculated, and that the Earth trajectory team validated, and that the flight engineer has reviewed so many times over the past 50 days that the numbers have become, in some deep cognitive sense, a kind of home. The ascent takes approximately 9 minutes. 9 minutes from the Martian surface to Mars orbit, a transit so brief relative to the 9 months of surface operations that it has the quality of a dream, compressed and slightly unreal, the habitat shrinking below them with a speed that feels violent after 270 days of the measured, deliberate pace of surface life. The rendezvous with the Earth return vehicle takes 6 hours. The docking procedure is nominal. The crew transfers from the ascent vehicle to the return vehicle, securing their samples, their personal equipment, their scientific data archives. The ascent vehicle is jettisoned. The Earth return vehicle's systems are brought to full operational readiness. At 19:23 local Mars time on Sol 270, the Earth return vehicle's main engine fires on the trans-Earth injection burn. The burn lasts 11 minutes and 23 seconds. It changes the vehicle's velocity by approximately 1.1 kilometers per second, enough to shift its orbit from a Mars-centered ellipse to a solar orbit that, in approximately 7.5 months, will intersect Earth's orbit at exactly the right place and time for atmospheric entry and return. They are going home. The 9-month window has closed behind them, not with a dramatic sound, not with a visible change, just with the silent arithmetic of orbital mechanics, the gradual divergence of the return vehicle's trajectory from Mars, the planet receding in the aft camera feed with the same indifferent patience with which it had approached in the forward camera feed 9 months and 270 days ago. What they carry with them is extraordinary in its multiplicity. The geological samples from 270 days of surface collection, including the sedimentary samples from Sol 231 that are stored in sealed containers in the sample return vault, and that carry within them a question, the most important question humanity has ever asked the universe, that will not be answered for months or years after they return. The physiological data from 6 human bodies that have lived through conditions no human body has lived through before. Data that will take decades to fully analyze, and that will form the empirical foundation for every subsequent human Mars mission. The operational data from 9 months of life support system performance, fault diagnosis, repair operations, and emergency responses, the accumulated institutional knowledge of what it actually takes to keep human beings alive on Mars, knowledge that exists now, not as a projection or a simulation or a model, but as a fact, verified in the most demanding experimental conditions imaginable. And they carry something else, something that is harder to catalogue and impossible to fully measure, but that is perhaps the most important thing they bring back. They carry the knowledge, not theoretical, not hypothetical, but operational and earned, that it can be done. That human beings, with the technology available in this era and the physiological fragility inherent in this species and the psychological complexity that makes us simultaneously our own greatest risk and our only genuine hope, can survive the 9-month window, can maintain the systems and the bodies and the relationships and the judgment necessary to live on another planet for 270 consecutive days, and then come home. This knowledge matters more than any individual data point or sample or measurement, because the first crewed Mars mission is not the destination, it is the proof of concept. It is the demonstration that the window can be survived, the template on which every subsequent mission will be built, the answer to the question that the entire preceding enterprise of robotic Mars exploration was ultimately asking. Can we go there and live? The answer now is yes, but the answer comes with caveats that the mission's data will spend years quantifying. The bone density losses are real and will require extended rehabilitation. The radiation doses accumulated are real and will be carried in the crew members' cells for the rest of their lives, a permanent biological record of where they went and how long they stayed. The psychological costs are real. The fatigue, the interpersonal stress, the sustained vigilance, the grief of months away from everyone and everything they love. And some of those costs will take longer to process than the physical ones. The unresolved medical finding in one crew member will be resolved within a week of Earth return, and the resolution, when it comes, is what the imaging suggested. Benign. A reactive lymph node, now resolving on its own, leaving behind only the memory of the 97 days of uncertainty during which it was carried. The crew lands on Earth 229 days after leaving Mars orbit. The total mission duration from Earth departure to Earth return is 912 days, just over 2.5 years. They emerge from the recovery spacecraft into the particular quality of Earth air that none of them, during all the months of Martian surface operations, had ever fully forgotten. The humidity, the complexity, the biological richness of an atmosphere that has been shaped by billions of years of life rather than billions of years of chemical equilibrium. The sky above the landing site is blue in a way that is almost painful after the butterscotch horizons of Mars. The gravity is 2.6 times what they have been living in for 9 months, and their bodies know it immediately. The familiar heaviness of home pressing down on systems that have recalibrated to a lighter world. They cannot walk. This is expected. After 270 days of Martian surface gravity and months of microgravity transit, their cardiovascular systems and musculoskeletal systems need time to readjust. They are carried from the recovery spacecraft on stretchers, transferred to the medical facility, begun immediately on the rehabilitation protocols that have been prepared for them. They will walk again within weeks. They will run again within months. The bone density losses will be largely recovered within a year through targeted rehabilitation and the natural bone remodeling that occurs when a skeleton is returned to full Earth gravitational loading. They are home. The window is closed. The 9 months that decided everything have been survived. But the questions they have brought back with them, the questions in the sealed sample containers in the sample vault, the questions in the physiological data, and the operational records and the psychological assessments, those questions are just opening. The 9-month window was the clock that governed survival. The decades that follow are the clock that will govern understanding. Because that is the deepest truth about the 9-month window. It is not just a survival problem. It is a learning problem. Every day inside the window, every fault and repair, and medical event and interpersonal friction, and dust storm, and anomalous output and difficult decision is simultaneously a threat to be managed and a lesson to be learned. The mission that follows this one will be planned with the knowledge of what the first one actually experienced. The mission after that will be planned with the knowledge of what the second one experienced. Each mission extends the range of human adaptation, refines the technology, deepens the understanding of what the window demands, and how to meet its demands more completely, more safely, more sustainably. The first crew to survive the 9-month window did not conquer Mars, they did not solve it. They did something more important and more durable. They proved that it was survivable. They demonstrated in the most concrete way available to our species that the distance between Earth and Mars is not just a physical measurement, but a human threshold, one that can be crossed at enormous cost and with enormous care by human beings willing to spend 9 months on the far side of it. The cost is real. The care required is real. The 9 months are real. And somewhere, in the sedimentary layers of a shallow valley on the Martian surface, in the rock face, where a geologist paused for an unscheduled 47 seconds and collected 4 samples that are now on their way back to Earth, somewhere in those layers, older than the first cells that ever divided in Earth's primordial oceans, the most important question in the history of science is waiting to be answered. The window was survived. The samples are coming home, and whatever they contain, whatever answer they ultimately provide to the question that has driven the entire endeavor, it is an answer that could only have been retrieved by the particular kind of creature that builds spacecraft and trains for years and accepts extraordinary risk and counts down 9 months on a foreign planet and chooses, against every survival instinct, to keep going. The clock has stopped, the window has closed, and everything that happens next begins here.